All right. Thanks for the introduction. So I slightly changed the title a little bit. Hopefully that's fine. So like Legion has mentioned, so this is a line of work that we started recently. So, well, instead of presenting certain solid results, it's more, well, I would say I will welcome any comments, suggestions, ideas after the talk, right? Okay, so let me first introduce myself. Li Jing has already done a good job there. I just want to say that do have this nice photo that I took many years ago. Hopefully, that helps you to remember my name somehow. So basically, if you look into this part of the photo, that's my name right there. All right, and then if you use one of those phones, you will probably see my name on your phone screen at least 4 times a year. And then for those of you who use Tencent, you're welcome to scan my QR code here, add me, etc. All right. Let me start. Since this is the first talk in this machine learning formal methods session, let me start with a bit of introduction on AI. Although I don't think these days we need a lot of introduction here. So the main message being AI is here. We see a lot of different impressive applications of AI, from stuff like playing Go game, or self-driving cars, or machine translation, or even generating artistic paintings. Okay, in all kinds of ways, AI seems to be interacting, taking over part of our daily lives. All right. Now, that's the good news, of course, but then there are also a set of bad news as well. So recently, people has discovered that AIs, which is sort of like a new sort of programming paradigm, are not that different from traditional programs. That is to say, AI as a program can be buggy as well. What you see on the screen is now a well-known experiment, which was done a few years back, that basically a bunch of researchers showed that by slightly temper this stop sign with certain graffitis or stickers, the self-driving car software, which is responsible for recognizing stop signs, will basically mistake this stop sign as a speed limit. For instance, speed limit to 45. And then hopefully you can see that is problematic, because by right, the stop sign is there for a certain reason. The car should be stopped before this, for instance, a junction. All right. If it's recognized as a speed limit, well, it will not stop. Okay, that's definitely a security safety issue. Right. That's just one example of all these issues that people recently discover on AI machine learning in general. Let me give you another example. This is slightly different from traditional software. So in this scenario, what was reported is a case where some police department trained a certain neural network to make predictions on all those offenders, meaning, well, criminals. How likely will they be coming back to the prison again after the first crime? Okay. And it turns out this neural network, which was trained based on real data, is discriminating certain races, meaning Black people, for instance. On the right of the screen, you see 2 examples where one is white, one is Black, and then somehow the Black folk is labeled with high risk, whereas the white guy is labeled with a considerably lower risk. Okay, of course, in the end, it turns out that the white guy is, well, visited the prison frequently. Okay, this, of course, generated a lot of concerns as well. In theory, all of these real-world data are generated basically based on whatever happened in this world, and that the world might not be fair. Meaning, yes, you might argue, indeed, in terms of probability, Black folks are more likely to commit a certain crime. But then, do we want to make that as a fact in a neural network that is making the future? If that is the case, you might just end up a system which enforces such discrimination. All right. This, of course, is arguable, but then let's say we do wish to have certain kind of fairness here. This is another example of such AI problems. Okay. In general, there are a number of different AI problems that we discover now. Okay. All of these problems are not new in a way, because if you believe that AI is simply a new form of programs, then if you have been doing program analysis or formal methods for some time, you will see that these issues are really not new. For instance, the AI example of misreading the stop sign is basically a kind of software bugs. Okay, whereas in the case of this fairness issue, well, it's kind of a bug as well. And in terms of other kind of problems that people discover, for instance, AI, machine learning, neural networks can be embedded with backdoors, meaning something like in normal scenarios, the neural network will be able to recognize you as you. But then if somehow there's some particular pixels are embedded into my photo, suddenly I can be recognized as Trump, for instance. Okay, that's basically a software backdoor. From that point of view, it's not really something new. Okay, softwares, we all know that it could be buggy, it could be critical for safety critical systems, and therefore we all agree, hopefully, that the softwares must be tested, analyzed, verified if possible. Okay, the argument here is, of course, we should do the same for AI systems. But then AI systems somehow are different, and then the differences will basically be our opportunities for new research. All right. So in terms of solving all these AI problems, just like solving all these software problems, there are a number of different approaches that we can possibly take. First, and then probably the easiest, is to do testing. Just like testing softwares, we should test AI systems. And then just like verifying safety critical softwares, we should have verification techniques which are dedicated to AI system. Okay, and then this is sort of where we are going in this talk. Okay, all right, so let me start with all these differences between AI system and traditional software systems. Let's keep in mind these differences so that some of the discussions later on will probably make more sense to you. Now, I will argue, no matter how complicated a traditional software system is, we can always consider it to be some form of a state machine or finite state automata, if you know something about these formal methods terms. Okay, basically it's logic. No matter how complicated it is, you can always think a program in terms of if then else, a series of if then else. Okay, from that point of view, a program is not beyond human understanding. The belief is that with patience, with certain experience, given any program, we should always be able to comprehend what the program is about and then be able to debug, verify the program if necessary. Okay. On the other hand, AI systems are different. These systems are not written based on logic. They are trained with with data. Okay. And then also, all of these neurons in a neural network are typically fully connected. So that means it's a spaghetti piece of code, if you know this term, which is basically this bad habit of writing program that we call spaghetti code. What I'm trying to say is that AI system is by nature a pile of spaghetti, which makes an analysis and verification basically infeasible. Okay, so that is fundamentally the difference between AI system and programs. And then this difference will have its consequences, as we will show shortly. Right. So in the following talk, well, there are all these AI problems that I mentioned. Let's focus on one particular problem. There are too many problems for me to talk about in one talk anyway. Okay, let's focus on this problem of fairness. Now, fairness is a particular property which is more relevant to AI systems probably than traditional software systems. In general, what we try to achieve is that whatever this AI system is try to predict or classify or whatever, there should be certain notion of non-discriminating. Okay, you might so typically when I'm reaching this point, some audience will argue, all these AI systems are trained based on real world data, and therefore, there's nothing wrong with the AI system. It's all these, are real data, real statistics, and therefore, well, it's reasonable. Well, let me just say that's not the belief that I have here. So the world currently is unfair. It doesn't justify that we want to have a future which is equally unfair. Okay, rather we want to train some system which improves the fairness over time. All right, so let's put that into a respect. Well, with that, let me try to formally define what is fairness. Now, there are a number of definitions for fairness. In fact, if you are into philosophy, fairness is typically a huge topic in philosophy. Let's take some really simple definition of fairness here, all right, just to get us started. So this definition of fairness is called individual discrimination. So it's simple. If I'm presented with two inputs to the neural network, okay, if these two inputs are exactly the same, identical, except in case of a certain protected feature. Now, what do I mean a protected feature? It means something like male or female, black or white. These features, which are typically associated with particular group, particular individuals, something which is often talked about in terms of fairness. Okay, so the idea is if two inputs to the neural network are exactly the same, except this one particular protected feature, then I would expect the neural network to produce the same result as well. Okay, that's one notion of fairness called individual discrimination. To put this definition in the real context, let's look at this census income database. So this is a database which is out of this German survey. And then basically it's a huge pile of feature vectors which are collecting all kinds of information related to individuals, like male, female, education, etc., etc. Okay, and then the goal of the objective of the neural network model is to predict whether someone has a salary higher than 50,000 per year. Okay, turns out this model is discriminating, right? So this is just one example of fairness, basically looking at two individual records, inputs, and then try to see whether they have the same output. There are all kinds of other definitions as well. Let me just give you another example, which I will briefly sort of analyze later on. So this is another example, which is called group fairness. So group fairness is a bit more complicated. So the idea is that, the probability of making certain prediction will be the same for different groups. What do I mean by different groups? For instance, recently there's this face recognition software issue, which was reported a lot on Twitter, Facebook. So the issue is basically these face recognition software out there. People found out that its accuracy is much better for white folks than that of the black folks. So basically, if this black dude is walking in front of the camera is more likely to make a mistake. Okay, and that is considered to be a violation of this so-called group fairness. So the idea is for every different group, the prediction of certain result should be more or less the same. I say more or less the same because we always put in this tolerant factor, which is epsilon, so that if they are only slightly different, that's probably fine. Okay, so let's say in the example on the right here, what I want is that a face recognition software or a neural network which is responsible for shortlisting resumes, it should be such that for black dudes and white dudes, the chance of shortlisting any candidate should be more or less the same, with a difference no more than 10%. Okay, and then with all these different definitions of fairness, the problem becomes, how do we, in fact, verify, analyze a neural network to be fair, to see whether it's fair or not, right? Let me go to quickly the first first idea that we tested. This is basically testing fairness. Okay, this is not that formal. I'm leading towards one formal approach later on. Okay, so this is a paper which is published this year. So basically, it's a fairness testing approach. Try to find out, inputs which show that the neural network is not fair, violating this individual discrimination definition of fairness. Okay, so we are looking after basically records like this in this approach, meaning two identical feature vector, which are different only by one feature, in this case, female or male, and then have different prediction. So this is a clear violation of this individual discrimination, right? The idea of fairness testing is not that different from program testing. The idea is it's a searching problem. So if you consider all possible inputs to a neural network as a huge space, the problem of fairness testing is basically to search through the space to identify pairs of inputs such that it shows a violation of this individual discrimination. Okay, a violation of this individual, an evidence of this individual discrimination, right? And of course, typically it's not sufficient to just find one such pair, because, well, I mean, neural networks, typically they are not fair, I would say. And then finding one pair doesn't really do much. And then often our goal is to find as many pairs as possible. And the goal is so that I can retrain the neural network so that it becomes fairer. Okay, all right, let's see how we do this. Just to give you some heads up, this problem has been tackled, by a number of people already. But it turns out all these existing approaches are basically trying to apply software testing techniques without any twist to neural networks. Basically, they treat neural network as one form of a program and then basically try to do testing there. Okay, so for instance, one of these latest approach before ours is trying to apply the idea of a symbolic execution to solve this problem. Well, I'm not sure if you know symbolic execution, but the idea is quite simple. That is, we try to generate at least one test case for each and every path, program path in a program, okay, through a certain constraint solving kind of approach. Okay, but then, like I mentioned already, well, in traditional programs, there's this clear notion of a program path, because there are basically a bunch of if then else statement in the program. This is not true in the case of a neural network. Yes, there are many passes in the neural network, but then because every neuron is typically connected with every neuron in the next layer, in terms of number of passes, it's huge. And it doesn't really make sense to cover every pass, because typically one input will cover many paths. Whereas in the case of program, one input covers one path. Okay. Whereas still this approach, which try to apply this successful idea in program to neural networks. So their idea is quite simple. What they try to do is to approximate a neural network with a simple program in a form of a decision tree or a simple linear program. Okay, so in this particular case, let's focus on the case of a decision tree. So what I try to do is basically to try to generate a decision tree which approximates the neural network to a certain degree, and then they try to generate all these test cases for covering different branches, different passes in a decision tree. Okay, and then they claim if all of these branches, passes has been covered, then, well, we achieve certain confidence in terms of testing the neural network as well. Okay, that's basically what this is trying to explain. Okay, well, in general, I don't know how you feel about this kind of approach. I find it to be a bit, well, ad hoc in a sense that, well, we know decision trees are so much easier, simpler than neural networks. And therefore, even if you achieve some kind of coverage based on the decision tree, it doesn't really imply a lot in terms of testing the neural network itself. Okay, so what we did is actually pretty easy as well, but then much more effective. Okay, so the idea is, well, neural networks are basically designed for optimization, particularly in terms of optimization based on gradients. Okay, so what we try to do is to consider this problem of finding counterexamples to fairness as a problem of optimization. Okay, so the idea is quite simple. So give me any input with certain label. What we try to do is apply minimum change to this input so that you will have maximum output change. Okay, and if somehow the change that we apply to the input is nothing related to the non-protected features, meaning I'm only changing the protected features, and then somehow if I got a different label, then obviously this will be an evidence of discrimination. Okay, on the top level, that is basically the idea. In terms of a particular technique, of course, there are a number of steps to make sure that we will find not only one or two such counterexamples, but also a lot of such counterexamples. And also all of these counterexamples will be different because in terms of retraining the model, different instances are better than similar instances. Okay, so the idea is like this. If I have to illustrate that, use a graph. We find first certain random input, which is say these black dots. Okay, these two black dots here represent two instances, two inputs, which are different only by one protected feature, male or female. Okay, and then since they are not a counterexample to fairness itself, let's assume these two dots have the same label. Okay, our goal is then basically through this technique called perturbation, meaning basically apply little changes. Little change meaning, for instance, changing one feature slightly. If it is 15, let's say I change it to 15.1. Okay, that kind of change. But then I want to change such a way that it causes maximum change in the decision, in the prediction by the neural network. So the idea is to move these black dots towards the decision boundary of the neural network. We keep doing this until one of these points crosses the boundary. And as a result, we have basically a pair of examples which demonstrates that this is a counterexample to fairness. Okay, and exactly how do we apply the change? We basically apply this idea of a gradient guided perturbation, meaning for each input, we calculate the direction of the gradient. For instance, let me use this census data as an example. If I'm giving this particular input, what I do is try to calculate the gradient of this X here. Now, this gradient says basically, if I want to change these values, these feature values in this record, how would I change it such that I can change the output in a certain way? Okay, one here means basically, well, if I plus one to this feature value, then, well, the prediction will be strengthened. Minus one here basically means, well, if I change this value, apply plus minus one, for instance, then it will be a negative change in the current prediction. Meaning, if it is now predicted to be more than 50,000, it will be less likely so. Okay, with this information, then basically what we try to do is change this record from X here to the new X here according to these gradients. For instance, if it is 1, the gradient is 1, then I will basically add 1 to the value here, 0 to 1. If it is negative 1, then we might make it negative 1. Okay, sometimes we have to do a bit of additional what we call clipping, just to make sure all these values are within certain range. because each feature vector is likely to have a constraint on its domain. Okay, that's basically the idea. All right. There are some more details in terms of how exactly this approach works. I will not give you more details, but then overall, the general idea is just like that. Okay, give any particular input, we apply simple change to these protected features in a way such that it will cause maximum change in the output, so that hopefully we will find a pair of inputs which violates fairness. Okay. Just to quickly give you some experiment results. These are basically, or ADF is our approach, obviously. These are existing state-of-art approach that we compare with. Just to show you the results quickly, we train the neural network models based on all these benchmark data sets. And then this is basically showing how many, such discriminating instances we are able to find, meaning count examples that we find with the same amount of time. Okay, if you look at the numbers, this is the number which is found by this existing approach that I discussed just now. This is the number that we found in the same number of time units, and you can see it's much more. All right, and similarly compared to other approaches, same story. Okay, and then if we compare this in a different sort of way, try to see how many, if we want to generate 1,000, discriminatory instances, how much time we want to take, then you can easily see that, this is our time. These are the times of existing approach. Basically, it's trying to say that we use much less time to find all these cases. Okay. The last results here basically shows that with our approach, we are able to generate so many instances. Retraining the neural network with our newly found instances improves the fairness of these models quite a bit. Okay. All right. So that's basically fairness testing. Now that's not formal, but then hopefully that gives you certain understanding of how this problem, what is the problem, and then how potentially they can be solved. Now let's look at how can we possibly verify a model against fairness. Now this is a much harder problem, of course. So let me say, there are so many impressive program and verification techniques out there, ranging from symbolic model checking, SIGA, abstract interpretation, etc. Okay. This might be arguable, but let me just say one of the key ingredients of all these successful verification technique will be we are able to construct abstractions of the programs, and we are able to verify properties based on the abstraction. Okay, so what I'm trying to say is that we need a way to abstract, and that has been basically made possible for programs. If you know techniques such as abstract interpretation or SIGA, model checking, etc., they made it really feasible, not only feasible but quite efficient. Okay, that's fundamentally possible because, if you believe me, if you're like me, all of these programs are written by human, and then they are the result of human logical reasoning, and then human logical reasoning is not that great. That means basically at any point of the time that I'm programming, I typically have a simple model in my mind because my mind is so limited. Okay, and that basically fundamentally is why it is always possible to construct simple models to verify certain property, because those programs are constructed based on simple models in the first place. Okay, now if you still remember the difference between neural networks and programs that I discussed in the beginning of the talk, that's not easy, if not impossible, for neural networks, because neural network work is this spaghetti pile of stuff which are really strongly connected. Each one is connected with each one, and therefore it's really hard to come up with effective ways of abstracting, making sense of certain part of the neural network. Okay, then how we do this? Well, there are still some ways of abstraction. So recently, what we've been trying to do is to abstract neural network using the idea of probabilistic reasoning. Okay, the idea is to view a neural network as a Markov chain, meaning we want to be able to construct a simpler Markov chain model, which is sort of as accurate as the neural network. Well, by sort of meaning there's always a certain error, since we know neural networks are so much more expressive than Markov chain. But then if there is a way for us to bound the error, that will basically allow us to do some verification with respect to the error bound. Okay, so in general, this approach that we are working on, the first bit of the approach has been already published in this year's ASC 2020. The idea is to systematically construct a Markov chain model out of, in this particular work, a recurrent neural network. Okay, so the idea can be illustrated at this high level with this diagram here. So basically, we try to group all those hidden neuron states into a number of clusters. And then based on all those clusters, we will basically measure, the frequency of one input transit from one cluster to another cluster. Okay, and then if we have sufficient number of such inputs, we will basically see there are certain, frequency associated with all these transitions, which we can turn into basically transition probability. Okay, in the end, we apply certain algorithm to generate certain Markov chain to represent that. Okay, that's a really high-level discussion, description of this approach that we tried. And then let me just say that it works pretty well. In fact, that in the experiments that we have done compared to all these existing approaches, well, it seems to be that we can indeed generate Markov chain models which accurately approximate neural networks to a certain degree. Okay, this is just quickly some experiment results that we have based on some real-world text or classification tasks. Okay, this in terms of this particular database, one is for sentiment analysis. Given certain review, I want to know it's positive or negative. The second one is try to see whether a text is a spam or not. Okay, this shows you some of the result. Well, this is a bit too much to read, but then let me just point you to the last, results that's here. Okay, basically this shows the accuracy of the model that we are able to generate compared to the original model. How often our results based on the Markov chain is the same as that of the neural network. Okay, and you can see that most of the numbers here are pretty high. There are a number of cases where it's not exactly very high, but then we figure there are certain reasons. And then in particular, in terms of these two real-world data sets, the accuracies are reasonably good. All right. Now, one central issue that I'm not really discussing here, but I would like to point out that we do have a solution is that, yes, we can always generate all these Markov chains, which are much simpler, which can mimic this neural network work to a certain degree. But then how do we quantify the errors which is possible in this Markov chain? That is, how do we say with confidence, for instance, 95% of the time, I'm pretty confident that this Markov chain will exactly have the same result as this neural network, because only with that kind of guarantee we can make further analysis. Okay. Well, let me just say that we recently proved the one result to show that that's indeed possible. Okay. This is a paper which we published recently in CAB 2020. So the idea is we calculate a bond. If you want to learn a Markov chain to mimic the behavior of a neural network, okay, we basically are able to tell you how many samples that you have to look at so that you are guaranteed to have a Markov chain model that is have certain level of quality. All right. I will not go into the details since I'm running out of time, but then you are welcome to look into the paper or talk to me anytime. All right. So let me come back to the bigger story here. So what I'm trying to say is that, AI systems are basically a new form of programs. And then just like traditional programs are buggy, may have backdoors, may have fairness issues, all of these problems are there in these AI systems as well. And then just like, traditional software systems must be tested and analyzed, verified with techniques such as abstraction, we have to do that for AI systems as well. Okay, and that's all I have to say. If you do have questions, well, let me know in a certain way. Yep.
So thanks a lot for the very interesting talk. So let me start with the question before we collect other questions. In the definition of fairness, so how much is this related to the notion of robustness? Because you mentioned this protected feature somehow, then intuitively being white or black and etc. Somehow they are, except this protect feature, they are close. So is it somehow formally linked to the notion of robustness?
Yes, some definitions of fairness is indeed quite closely related to robustness. If you look at this individual discrimination definition, it's pretty closely related to robustness. In fact, if you look at the title of the paper that we published this year, basically we are doing fairness testing by adversarial sampling, which is a way of basically doing or finding problem with a robustness problem.
Yeah, in that part, but I rather wonder the part where you start with this protected feature. So say being white or black. So how is the definition of the distance between, say, they are the same except one of the feature being different?
If you're referring to this definition of, say, individual discrimination, then it's simple. We just look at two inputs. We look at two concrete inputs, and then if one feature vector says this guy is black, that guy is white, and then all the rest are the same, then we say they are different. And then if you are referring to this group fairness, it's a bit more complicated. We basically have to look at all black dudes and then all white dudes, and then see, among all the white dudes, if how many of them, for instance, in general, will be basically shortlisted, for instance, and then compare that to all the black folks, and then the differences between these conditional probability.
I see. So in the first part, essentially, say the protected feature is essentially provided as an input to the problem, right? So you just take one of the protected feature, say take it to the pair black or white, for instance, right?
Yep.
Okay. So I also see a question from the other source. It's probably you could probably explain again a bit how and why you use the gradient approach. So in the first part of the talk to perturb the input for generating the solution. So why use the gradient approach?
Well, so that idea came out basically, we are reading all these papers who basically try to propose all these testing coverage ideas or symbolic execution for a neural network, etc. And then we feel that at least in terms of fairness testing, that doesn't make a lot of sense, because neural networks are different from programs, and then sort of we want to prove to ourselves we can solve this problem much easier. Just use all this gradient-based robustness testing approach, we can do a much better job without using techniques such as simple execution, etc. And it turns out to be the case.
Okay. So another question from one of the students is, so let me read this question. So it's about whether you have results applying pre-processing. Any results of pre-processing or in-processing? In-processing?
I don't quite get the question. How's this related to fairness? Meaning pre-processing, in-processing might introduce or reduce a certain fairness?
So let me try to interpret this question as well, because we have this question from another channel. So does neural network itself have this preference, or does it describe the preference of the data set?
Yep, I would say it's the latter, meaning it's I would believe, well, neural networks are not that evil, at least nobody intentionally try to build discrimination into the model. We actually have one work try to do that as an attacker. But in general, I would say all of these existing problems, it's basically discrimination in the data itself. So as I mentioned, this world is not fair. So you can imagine, all of these data collected in this world is not fair either. Black dudes maybe statistically are more likely to commit crime. But then, it's a question on whether you want to make a model which always make such kind of prediction. Okay, if you have been watching, TV such as Westworld, there's a huge discussion in terms of whether that's moral. Yeah.
So, so let me take a chance to ask questions from the audience. So anyone wants to propose a question from the Zoom audience? So I quite like the notion of the protected pair and etc. It reminds me to think about the differential privacy methodology.
Yep.
So that is also quite related to robustness and in particular to the fairness notion that you're proposing. So say being white or black and kind of protected attributes, they can be considered as the privacy that is to be protected. But then you want to guarantee how the output, although are close. So independent.
Well, that's exactly right, and that's really insightful. So in general, this idea of group fairness. In general, it's called independence-based fairness. So basically, it says certain features. Well, if you take the privacy point of view, basically there shouldn't be certain sort of entropy or information from this protected feature to the decision. Basically, if you take that kind of view, then yes, it's indeed quite related to this differential privacy kind of idea.
Yeah, and because I think I would be very interested in looking at the connection with different privacy, and because there are other different focus of the differential privacy framework, and there are framework where they have different kind of secret pairs and etc. That sounds to me quite related to your I mean, from the intuitive sense. So let me ask, I mean, sorry, let me ask, I mean, say there are other people investigating different privacy of neural networks. So have you looked into this, and how much does this relate to your framework?
Well, so there are a bunch of people researching, looking into differential privacy for neural networks. A lot of them, typically in terms of privacy issues. So neural networks, just like other kind of systems, might have privacy issues. Meaning, you might be able to deduce, based on certain results, whether my data is in the data set or something. That kind of privacy issue. And typically, it's done related to privacy. In terms of fairness, nobody look at differential privacy yet. But it's quite related, as you say, yes.
So still no question from the audience? So I see another question from our other source. That is easy to answer, but you could clarify the framework again. So say, is there any relationship between the algorithm finding the unfair example and the algorithm that finds the worthy samples?
So from the high level point of view, it's the same algorithm. So basically, yeah, I mean, you can basically regard this individual discrimination as a special case of robustness issue. And then, yeah, you can basically use the same algorithm to solve them.
So, well, if there's no other questions, still I want to ask questions because we have a lot of time and I'm very interested in your talk. So I like the words. You have a neural network, you have fairness, you have testing, and then you somehow reduce it to Markov chains. But I don't get the idea. How have you done? I mean, what does the states represent, and what does transition represent, and etc. It's so interesting. Could you give a bit more detail how you abstract, say, the layers to states in the Markov chain, and what is the intuitive meaning of a state and the transition in the Markov chain encoding?
I see. Well, I was told that I should talk no more than 40 minutes, so I planned for that. That's a paper basically we are exactly working on right now. So we just I just did some proof to show that we can construct certain Markov chain models so that we can show certain fairness, etc. So if you can still see my screen. Yeah. So I'm bringing up this graph that I'm working on basically. So the idea is, well, the simple idea would be, I will, given some neural network, I will keep sampling neural network, meaning basically producing inputs in an IDD way, meaning basically randomly, uniformly generating all these samples. And then we will feed those inputs into the neural network. And it depends on what kind of neural network you use, then we can observe a trace. Now, if it is a simple feed-forward neural network, then basically this trace composes of the status of all these neurons on the way. If it is, say, recurrent neural network, then it's a more complicated trace, but nevertheless, it's a trace, okay? It's a trace which has inputs, intermediate neuron states, and then the label, okay? Then what we do is basically, in the simplest possible way, what we do is count, like how many times I'm transitioning from this input to that neuron internal state to that label. And then if I collect sufficient number of such traces, then basically we can estimate, overall what is the likelihood of transition between these states. Okay, and then to make that estimation, there are many different ways. For instance, the simplest possible way will be basically frequency. If I visited the state 100 times, and then out of the 100 times, 60 times I'm going to this other state, then I will basically say probability 0.6. Okay, there are more sophisticated ways such as Laplace estimation, Gauthierin estimation, but nevertheless, it's basically the same idea. I want to use those to estimate the transition probability between all these states. Okay, and next, with that, basically we are able to generate a Markov chain model. Now, the interesting bit in this work that we are doing currently is to prove that if we have sufficient number of samples, depending on the transition probability, depending what kind of properties that you are working on, etc., we can guarantee that the model that you generate, if you verify fairness based on that Markov chain model, it applies to the original neural network. So basically meaning, if you have this Markov chain model, then based on this Markov chain model, for instance here, if I have this M state, which represents a male, and then, sorry, if I have this F state, which represents a female, and then, then basically I can calculate what is the probability of predicting one from female, and then what is the probability of predicting one from male, okay? And then I make a comparison. Then I can basically tell whether fairness is satisfied by this model or not. By this model here, I mean this Markov chain, okay? with that theory that we prove, what we try to say is that this result that you get from this Markov chain, you can basically apply it. We can be sure that it applies to the original neural network. So meaning basically, if you say this fairness property is violated based on this DTMC Markov chain, then the neural network is not fair as well. And then after that, we can do further analysis. Like for instance, if I want, I can look at one particular neuron hidden at a hidden layer, and then quantify like how much impact this neuron has on the prediction, whether it's sensitive to the feature of male or female, whether it's sensitive to the outcome. If I can find out that, then basically I can, have a way of maybe tuning the neural network a little bit so that it's more fair. Yeah, I'm not sure I made it clear. This is an ongoing work.
Yeah, I think it's yeah, pretty much. So let me say in the figure 1, so the male and female, the two nodes, the two states in the middle. So how, I mean, do they correspond to some hidden layer, or do they correspond to the protected attribute that you take as input? I mean, how do you get the probability 0, 1 from the start to male, for instance?
I see. So the first part of the question, so this male, female, these are basically states representing the protected features. So in order to be able to verify fairness, I will minimally need these states which represents these protected feature, and also the labels, because otherwise I can't do the verification. Okay. Yeah. And then the probability distribution is basically an estimation based on all this sampling that I do. So I'm basically uniformly sample out of all these possible inputs, and I'm counting like how many times it's a male, how many times a female, and then how many times from female I will transit to a result of say 1, how many times I'm transiting a result of 0. That gives me the probability. Now this model here doesn't show the states for the internal neurons. Hopefully I have one later. So like this model here, then I can look into all these status of the internal neurons. I can basically use the same way to look into the probability transition between these internal states. And then that allows me to do more analysis, basically.
I see. So I assume for Fn or Cn, so if there's no loop, then you have a Markov chain that is also acyclic. And then Rn, you will also have loops in the Markov chain.
Well, Rn is a bit more complicated. So the ASE paper that I mentioned, we do deal with Rn. In general, the complication is in terms of how to abstract those loops. So there are still fixed number of hidden neurons. So it's possible to abstract these hidden neurons into finite number of partitions, for instance. But then the abstraction itself, well, we can do it. It's just that we don't have a theorem to say we can have certain property preserved yet.
Very interesting. So I think there are a group of people working on, say, conditional logic for probabilistic Markov chains. It sounds quite similar. It could be useful for your framework, because they consider conditional logic, say, assuming phi holds, then the probability of psi and etc. It's that could be something interesting for you.
That's quite related indeed. Yes.
Okay, so well, let me ask whether they have some questions from the audience. So if not, I think you have information of our invited speaker, and if you are interested in this, I found quite interesting. So you could just directly contact Professor SunJun, and he will be very happy to talk with you and answer your questions. I assume. And
always.
let me thank SunJun again. So thanks a lot for the exciting talk, and we appreciate your time and your talk. So
Thank you.
thanks.
Yep, thank you.